I was looking at this. One thing they don't cover is your integer, your long word math. I think the book covers the range for using a word math. Of course, we have 16 bits, but when we use sign math, we sacrifice the most significant bit for the sign, right? We talked about that. This is something called 2's complement, which gives us 2 to the 15th combination, which is where the 32,768 to 32,767 come into play. And why we have one more negative when we have positive is because what?
Yeah, sign.
Because 0 eats up one of your positive slots. Because 0, so if the most significant bit is a 1, and we're using signed math, it's assumed to be a negative number. Right? You understand that? If the most significant bit is a 0, it's assumed to be a positive number. Well, the problem is, if you got 0, the most significant bit is going to be a what? A 0, but 0 has no sign. 0 is considered it has no weight, so it's considered not to be either a negative or positive number. So this is why we have one more negative combination than we have positive combination, because 0 eats up one of your positive combinations. Long word math, we go out to, also called double words. Microsoft refers to 32-bit numbers as double words. Alan Bradley refers to them as long words. This jumps us up to 32 bits. If we're using unsigned integer math, if we're using signed integer math. Does that make sense? Now, if you're doing unsigned math, you don't pay attention to the overflow bit or anything like that because you're doing unsigned math, right? Understand that. And you get full access to the thing. If you're doing signed math, then that's where your overflow bit and your signed bit would come into play, where you would come in inside your flag. So now we get 2 to the 31st. Which means we could have we could have an unsigned assigned integer numbers from minus 2,147, 2,147,483,648 to a minus. I've got this backwards. I've got to put plus. I just did this today.
Big numbers, Mr. Raymond.
We got bigger than that. What do you need, Joseph?
Big numbers. No electrical guys here already for next to us, those 5-week courses.
I don't know. They would be in the next 2 labs if they're here.
Yeah. Got 6 people. Okay, thank you.
All right. From 2,147,483, 2,147,483,247. By the way, I couldn't find it. I'm sure it's in the MicroLogic 1000. But for the 500 series, what you do if you want to deal with long words, you set bit 14 to 1. If you're dealing with regular words, you set bit 14 inside the status register for a 0. Now you have to remember though is that if you go to long words, then your integers are going to jump in groups of 2 addresses, right? So we go 0, 2, 4, right? You understand that? So you'd have to jump 2. I didn't have time to put it up here, but on the MicroLogic 1100, you have an L register. I'm sorry, an L, you have a set of L register files. So what you would do, you would specify your math to be formed in the L data file, right? You understand? Yes or no?
Say L one more time.
Well, we got M7.
Yeah, L.
Okay.
L data file.
Yeah, so what I would use is I would use an L. I would use like L:0. I need to check and see. I'm pretty sure it's just L. So on MicroLogic 11, you don't have to. So on 1100, MicroLogic 1100, you don't have to set that bit. You just use the L data files instead of the what? instead of the N data file. That makes sense? If you specify the L data files, then it's gonna do 32-bit math, long word, integers.
And like we addressed the 187 colon.
Then it's gonna be, if you, on the MicroLogic 11, on the 1100, if you do N7, it's going to be, 16-bit sign math. If you use the L register, and I'll look up the number and give it to you, but yeah, this is available. By the way, all these data books are available to you on Blackboard, right? You understand that? I'm not sure about the MicroLogic 1000. I didn't have enough time to figure out what you do on that one. It doesn't support a long word. So since it doesn't support a long data file, a set of data files, then odds are it might use the same feature. It talks about 32-bit integer math, but I couldn't find in the short time I had. I should have did this the other day, but this was just something that popped in my mind this weekend when I was looking at get ready for the class. So the MicroLogic 11,000 or 1100, I'm sorry, which is the new ones, the newer small ones that we have here. This guy here supports a L data file, and I couldn't find it. I opened up all the manuals.
And you said that was just a L colon?
I'm not sure. I need to find it again. So I did a scan for data files. To get the list of data files, but I couldn't find it. I know it's in here somewhere. Oh, this is, I opened up the wrong manual, what it is. I opened up the PLC manual and not the programming manual. So MicroLogic instruction set, reference manual, this is the one I should have opened up. Sorry guys, it's the boss. I'll call back. So it don't look like. So here's the data files that are available with us with the MicroLogic 1100. Yeah, and the L doesn't specify. So it looks like the L is just an L code. So the N, it says I need to use N what? Yeah, the F I need to use what? A. And then this is string data, by the way, which is ASCII code. This is L file, and then it says we have to use from 9 to 255 long word files and general purpose files for integer data. So on the MicroLogic 1100, these are integers, right? Understand that? What's an integer?
Whole sign.
Also, the 1100 adds a message data file where we can actually the 1100's got an little LCD screen on it where you can literally send information up to that little screen, which is pretty neat. So you might support more data files. So what you need to do to figure out the data files that your PLC, the version of the PLC that your Allen Bradley PLC you're finding, you need to go to the instruction reference manual, right? And these are given away free, by the way. Allen Bradley gives them away free. If you go to Allen Bradley's website, I think you go to support, and then you can download any instruction set file that you want for the PLC that you get into. Now, all we do is teach we got the 1100s, which Randy got set up right. We have the 1000s, and we have the SLCs or the SLC 500s. It's the ones that we have So there's several variations above that, that add more instructions. Just about every one of them I know, though, you can, are basically the same, right? 'Cause we went over there and looked at the ceiling. So even if you went up to the next, the 5000 series programming language, then everything we talk about would still be available to you. The only thing we don't have time to teach in this class, of course, is programming in the text language. We program in the ladder logic language for both. So that if we looked at the instruction reference for the so there's the 1000. I couldn't find it, but that's what you need to do. You need to see what's available to you, because limiting your integers to 32,768 might be limited by some applications, right? But if we use these long words, then we can get all the way up to over 2 billion, which should satisfy most everything. And then if we need more than 2 billion, then we would have to go to well, we'd have to go to floating point. Floating point gets us up to extremely large numbers, because floating point you can use scientific notation. So it's like your calculator. If you exceed the range of your calculator, it automatically shifts into what? Scientific notation. But the main thing we're going to look at today is the next chapter, which I think we got 2 more chapters we're going to make sure we cover in this class. And
Which one of you have systems?
a lot. The review's up there. I know I put it up there late and I didn't send out a, but so this chapter will be on this. Yeah. And this is where I realized that we didn't talk about doing 32-bit integer math. So your FA register can do signed numbers, and then it can also do exponents, right? You understand that? But these guys take up a lot of space. And by the way, a lot of your reference manuals will actually give you the time that each one of these instructions require. So what we're going to do in this class, in this lab, we'll look at the logic instructions, and then our bit shifters. So logic, we know how to do contacts, but the problem is when we start dealing with a lot of contacts, it starts getting very confusing, right? You understand? What we can do is we can combine all these inputs into a logic instruction. So each logic instruction can do logic on up to 16 bits. Right? You understand that? And then we can combine those. So our basic logic instructions, we have 5 basic ones. We don't consider the exclusive OR to be when you get into digital, we don't consider exclusive ORs to be a basic logic function. We have 5 basic logic functions. We call not, we have ands, fors, right? Then we have what? Nands, nors, and nots. That's our 4 basic logic. And all other logic, it can be formed from those 5 functions.
You said not, and, or, and, nor.
Yeah, 5. The exclusive OR, we don't consider it to be one of the basic logic functions. In digital, this is actually performed by multiple headings. It's what we call combinational logic. So when I do an exclusive OR, I can only exclusive OR 2 inputs, right? Everybody understand that? Or 2 contacts. Well, it would still be considered inputs. But what we can do here is we can exclusive OR 16 bits with 16 bits. Right? Does that make sense?
16.
16 and 16.
16.
With 16.
Okay, you said something.
Well, when we do a logic, when we do this, when we do logic, most of the time we're dealing with 2 things, right? So if I was gonna come up here and do, an exclusive OR, I'm gonna do it on what we call contact A and B. But I'm on exclusive OR, it is still exclusive OR with A and B, right? You understand? So what I can do with these logic instructions is I can exclusive OR 16 bits with 16 bits. You're still only working on them 2 at a time. Everybody understand that? But we can still exclusive OR 16 bits with 16 bits. Oops, they won't do that. So normally what we would do is, if I was going to do an exclusive OR, and I'll draw the logic. Everybody knows the logic, right? The logic symbol for exclusive OR. So it's basically an OR gate, but we put a ghosting on the input, and we come up with this, and this would be exclusive OR. Okay, but here I'm on exclusive OR, we'll say A and B. Okay. Well, what I would have to do is, if I wanted to exclusive OR more contacts, is I would have to use, and of course we implement this. And what does this show? But what does it show? It shows us when the 2 inputs are not equal. So an exclusive OR will give us a low output or a false output if the 2 inputs are equal. It would give us a energized, or whatever we want to say, output if the 2 inputs are not equal. So the symbol shows you what you get if they're not equal. But I can only do 2 bits at a time. So over here, this would be like this, right? So if I was to come up and develop what we call a truth table, some people call them function tables, right? And normally what we do in digital is we assign the inputs starting. If we're doing generic, now in real life, they're going to give these things labels. Just like when we do our motor controls, we give these things labels, right? You understand? And what does the labels do? Well, they help us figure out how that thing can work. So instead of me just over here having a contact, input 0, input 1, I come over and I say, okay, this is my start, this is my stop, this is my right, you understand that? And it allows us to do that. So generically, in digital schematics, these A's and B's are going to be given names. Right, you understand that? So I might be wanting to label, take my stop button and then exclusive OR with something else. Well, what we do over here on A and B is we would actually write the name, right? But generically, when we're dealing with logic, so we can do what we call truth tables, we assign the inputs. This is just for teaching, right? You understand that? We assign it letters starting in the lower letters of the alphabet, and our outputs we usually start up with high letters. Does that make sense? So I might call the inputs A and B, but I wouldn't call the output Z. I might call it X, or I might call it Z. Does that make sense? Okay. So if I was going to do what we call a truth table for this, we got 4 combinations we can put on here, and all we usually do is just start counting. I know I can do 4 combinations because I know I've got 2 inputs. So what we can do to kind of figure out the number of inputs, we just look at the number of inputs and we raise 2 to that power. So how many inputs do I have? 2. So 2 squared is what? 4. So that tells me how many entries I'm going to have in my, what we call our truth table. Then we come over here on the right-hand side and we put what we would get out for these 4 input combinations. Now, truth tables and Chernoff maps are fun, but sooner or later, you're going to have to learn Boolean algebra, because the problem is if I go to 4 inputs, that's 16 combinations. If I go to 5 inputs, that's 32 combinations, right? Right? Y'all understand that? So our truth table gets so long that it don't make any sense. It's also good with Chernoff maps, because for every combination in a Chernoff map, you've got to have a box, right? You understand that? I think y'all learned Chernoff maps So truth tables are good for teaching logic. Karnoff maps is good for teaching logic, but you need to learn Boolean algebra. So with Boolean algebra, you set up a math equation for a circuit and then you try to reduce it. And what's nice about Boolean algebra is that if you can reduce the math equation, you're actually reducing circuitry, right? Does that make sense? So what would we have? But what I'm dealing with here, I'm still only dealing with two bits. So what would we get here? So here, if they're not equal, we get what? A high. Okay. So what I would do is this would give me my truth table. So they're not equal. They are equal here. They're not equal there. They're not equal here. They are equal here. In this, we would say, okay, so here the output would be energized. Here the output would be de-energized, which would be the same thing in both. But I'm still only doing this with two bits. What if I needed an exclusive OR, a C and a D and an E and a G and an F? Y'all understand that? But what we're doing now is we're getting into multiple bits. So what we can do with this, and we're still working on this truth table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Well, let's say I come up here now, I can come up here and I'm just making up stuff. I can exclusive OR up to 16 bits, right? Y'all understand that? But we're still working on them one at a time, 2 bits at a time. Okay. So this is what we can do with these logic instructions. So if I do it with contacts, I'm going to be working on 2. But if I do it with words, I'm going to be working on 16 bits at a time. And where can those words come from? Well, those words could come from 2 inputs, right? 2 16-bit inputs. So remember, and we would have to look and see how Siemens does this. So Siemens plays, their inputs are set up in groups of 8s. And Allen Bradley's are set up in groups of 16, right? So Siemens does bytes, and then they might do words. I need to look up like I said, I'm learning that myself. So what would I get here? Well, they're not equal here, right? They are equal here. They are equal here. They are equal here. They're not equal there. They're not equal there. They're not equal here. They are equal there. They are equal there. They are equal there. They're okay. Not here. Not there. And that would be the result. Oh yeah, they're not equal. No, yeah, that's right. They are equal though. I might have said not equal, but they are. Okay, but what I would do, so I would have 2 registers I'm going to use, right? So understand that. I would get one pattern from one location. I would get another pattern from the other location. And then we use the exclusive OR instruction. Would this be an input instruction or would it be an output? Input. Yeah, this is input. We're going to use this to make a decision on when something happens, right? You understand that? So these would be input.
Now, the 2 inputs always be synchronized?
What do you mean?
Begin at the same time?
Yeah, well, they exclusive OR just like I would do it.
I know, but is there a chance that input A would start before B?
When we say inputs, well, that's something that you would have to figure out. I mean, when this instruction is executed, whatever's going on those registers will be what we get, or those data files, right? Whenever the instruction is. That answer your question? Yes, no?
Yeah.
So it says the basic instructions, and we'll come up here and look at this. So we have these basic instructions. We have a not, we have an and, we have an or, and we have an exclusive or. What about the NAND? What about the NOR? And what about the exclusive NOR? But how would we get them? If these are the only ones Allen Bradley supports, how would we get them? They're input instructions, right? You understand? So if I was to come up here on my example and did an exclusive if I did an exclusive NOR, oops, where's it at, guys? Oh, it's the first one over there. So what's the difference between this and an exclusive NOR? Now, the exclusive NOR would have this symbol right here.
Plus, you have to have two.
And my true table for the exclusive OR, we'll call this Z. What I'm going to do is I'm just going to come over here and just do what? I'm going to just come over and do what? Opposite. Well, yeah, so what we would do is we would combine two. So my first one would be an exclusive OR, and then I would feed that into a NOT. And the combination of these two inputs would give me what? Yeah, exclusive NOR. So how would I get an AND? How would I get an AND? Well, I would AND two. I'd add my two, and then I would not. I'd run it into a NOT, right? And that gives me an AND. That gives me a NOR. That gives me exclusive NOR. So it would take two input instructions, but that's okay. It reduces the instruction set by several. Cascade, so the book uses the term cascade, which means we're going to hook them in series. The NOT input instruction to an AND, and we end up with NAND, right? If we NOT the output of a NOR or the results of a NOR, we end up with, or we end up with a NOR. If we NOT the output, if we NOT the answer to the exclusive OR, then we get an exclusive NOR. So we're going to create a PLC ladder diagram also that uses our bit shift instruction. With bit shifts, we can do what? Shift left or shift right. These are cool. What we're going to do here is also look at the data file. So what we're going to do, I think, in these examples is we're going to shift the data file. Our bit files, I'm sorry. Everybody okay on their bit files? What's our bit files?
B3.
B3 and B10. Supports it. I don't think Logic Pro supports B10, I don't think. But I think all our PLCs down there do, the actual PLC. We set the shift left or bit shift right instruction to its starting position. So we'll see how we do that. First of all, the logic. Allen Bradley, the RS Logic's 500 series PLCs have 4 logic gate instructions. And these are input instructions. So where do they go? In our ladder? Inputs go on the left. They go one side. Not and, or, and exclusive. Is everybody okay on these instructions themselves? But what's the and? The logic gate, the logic looks like the letter D, uppercase D. But when we look at this symbol, we're going to say all highs equal a high. Now, in digital, we can AND as many, basically, as we do. On PLCs, we're going to AND 2 bits at a time. So your logic function is going to deal with 2 bits at a time. We'll show you how we can string these together to get as many ANDs as we possibly need. The OR symbol and of course the term we use here is any high or any true equals a high.
And we don't have a term for an exclusive OR.
But exclusive OR, if the inputs are equal, we get a what? I'm sorry, if the inputs are not equal, we get a high.
How you doing?
Now, even in digital, exclusive ORs can only have 2 inputs. And then, of course, this is a symbol for a NOT. We could set it either way, but I guess I should spell out equal right there. Put an equal sign.
So anyhow, of course, the motor control will say, you both have to be 1, right? Understand? To get a watt of 1. Here, any 1 will equal a 1. So we probably need to rephrase that here. Digital logic, we're dealing with voltage level flow here on the input. For PLCs, we're not actually dealing with voltage levels. If we look at these registers, we're looking for digital information, 1s and 0s. Now, on an input, if you got a high coming in or a voltage coming in, you're going to get a 1, right? You understand? If you get a ground coming in or a 0 coming in, you're going to get a 0. So even in PLCs, these inputs give you 1s. Your PLC interprets a voltage and the absence of a voltage as being 1s and 0s. So when we start looking at these data tables that we can look at, or these data files that we can look at, yeah, when we come up here and look at these, what we see is we see what? 1, 0. Okay. So this is B3. So B3, it would be 0. Let's look at B2. By the way, when you bring up any of these data files on Allen Bradley, if you look right here on the left-hand side, you see this little scroll button. Well, what can we do with that? We can go to any other data files once we open up. So it really doesn't make any difference which ones you're using. So we'll go down here and look at B10 if I can find it. Okay, there it is. And oh, it's not in run. Oh, it is in run. Oh, I'm sorry. I like it. Okay, so here's inputs, and so these are my push buttons. Can y'all see them? So we can actually look. So that's my stop button. So I'm using a normally closed contact. So there's a voltage coming. We're using 24 volts on this PLC. This is a 24 volt input module. Right now we have them hooked up for syncing. So what does that mean?
Syncing connected to the sourcing.
Yeah, so that means my push buttons are hooked up for sourcing. My inputs are hooked up for what? Syncing. Y'all understand that? So it means I take power and hook them up to my switches. So I'll use plus 24 volts for the common on my switches, right? You understand? And then every time I press a button, it's going to put a voltage into this thing.
Can you say that again? Input is for what now?
You take sourcing input devices and we hook them up to syncing inputs. So if you go down there on the, and some of your modules, all the modular PLCs I know of you buy either a syncing input module or you buy either a sourcing. So if we went down and looked at the 504s down there, the SLC 504s, and we looked at the input module, it's got syncing on it.
What's the output? The output is,
The output is either gonna be sourcing or syncing.
oh, they can be either one.
Well, it depends. On most modular PLCs, you specify what type you want. A lot of your fixed PLCs or your hybrid PLCs, you can specify whether you want syncing. You establish the common.
So what are we gonna, what is the norm? Is it,
Well, the norm depends on what device you're trying to control. What does that device need? Does it need a ground or does it need power? Okay. If that device needs power and we hook it up to ground, then we would want to use a syncing output. Yeah, syncing output. We shifted over to syncing output. If your output device needs power attached to it, then we would use a syncing output. Yeah, what we're doing is we know we have to provide power. We know we have to provide power.
right?
Okay. So we need 2 wires to provide power. Y'all understand that? Okay. So when we hook up, it depends on the PLC. So when we hook up an input device, let's say I hook up a push button. Well, what are we going to put on this side? So here, this is going to come over to my PLC input. Okay, so this is, let's say this goes to input 0/0. Well, if I come over here and put this up to plus 24, okay, it's got the power to it. So this guy here is going to sync that. So this guy, the input port is going to use, so the input port would use this as the common. And then my input device would hook up to this. Well, over here on this side, the switch is going to be hooked up, let's say it hooks up to plus 24 volts. Well, that means my input over here has got, what's this plus 24 volts looking for? It's looking for a common.
Right.
Okay, so if this guy is hooked to common, so it's syncing, this guy is hooked up to power, so it's sourcing. Okay, y'all understand that? So that means if on all my switches, if I hook up power to my switches, I use that as the common for my switches. And that, for some reason, people get common as 0 volts. Common is what you make it. So what I would do is I would come down here and all these switches, I would just put a jumper between them. And then what am I using over here? So these guys are what? These guys are sourcing. So what do I have to hook this up to? I have to have a syncing input. Because I've got the power, so my input has to provide the what? The common. Now you're not hooking it up to common. You're going through an electronic circuit here, so that's the input circuit right there. Right? You understand that? And then the other side would connect to common. And so what we're saying is a sourcing input device has got to have a syncing input on our PLC. Okay, so let's say I move over to the output side. And I want to connect this motor over here. I want to connect it up to some voltage. And this is plus. Okay, you understand? All right. So what's this guy got? What is it looking for over here? It's looking for a ground. So that means my input, if I use a sourcing output device, right, I've got to have a syncing output. So they got to be just opposite. So if my equipment uses a positive common, then my inputs have got to provide the what? The ground. And that all depends on what you hook up out there. And that's what you got to look at. Now, AC, this only comes into play when you're dealing with alternating current, when you're dealing with DC. AC, there's no such thing as syncing and sourcing. Because AC is, we establish anything we want to as common, but it's still AC. And really, AC has no polarity, right? You understand that? Because why? It does have a polarity, but it's not obvious to us because it's switching so dang fast. You know, it's 60 cycles a second. Right, y'all understand that? That means that sucker is changing polarity every 1/60th of a second. It changes polarity, or every 8.333333 milliseconds. DC though, if you're dealing with DC, and more we're going to DC only input, and we're going to 24 volts. And why?
Oh, that's actually.
Yeah, it's below the NAFTA 70E standard. So that means if we're below 70E, then we're not required to use any safety equipment. Huh? Well, any PPE, you're not required to use any special PPE. Of course, then you're up to what the employer requires, right? So out at US Steel, you can't hardly work on anything without your hard hat on, your safety glasses on, and your metal parcels, right? But that's company policy. If you were working at US Steel and you were working with the 1100 PLCs, that's 120 volts. Then you would probably be required to wear a safety glass. When you make measurements, anything over 240 volts, when you make measurements, you're supposed to use insulated gloves or leather gloves, leather palm, at least leather palm gloves. We're going to have to change the motor controls around a little bit. Require that.
To be honest, I don't think I ever ran into using DC,
Well, on inputs, but it's moved. The PLCs are slowly moving. Most of your hybrid PLCs or your fixed PLCs have a DC power supply built in.
Oh, okay.
24 volts. It's not designed to run outputs. It's designed to run your inputs. Okay.
We had some that do 250 volts.
Yeah. And so if you got AC input modules, and what you're going to do is you're going to do what's if you're going to power up off the system, then you got to power up on what's there. So odds are those guys didn't have a special power supply. They just powered off the system that they were using. Yeah, US Steel has a lot of 250 DC to run the big motors.
Does the input dictate the output?
What's that?
Does the input dictate the output?
No, they're completely separate from each other.
So you can use
Well, depends on.
sourcing on input and sourcing on output?
Sure. If that's the way your system is wired up, or if that's the way your plant wants to do it. A lot of times it deals with how the engineers at the plant want to wire stuff up. The 1100 and the MicroLogic, they got inputs, they group them in two groups. So you can set up one group for syncing and set up the other group for sourcing. And that's also true on the 1100s. Both of them have relay outputs. What does it mean, relay outputs? And everyone's got their own common. So literally, if you got the MicroLogic 1100 or you got the MicroLogic 1000, you can set up input 0 as sourcing. You can set up the other one as syncing, or you can use AC, which is really, really neat. The only problem with relay outputs, they have a lot of advantages, but now you're switching back over to an electromechanical device, right? They use these little read relays, which means contacts could freeze. You screw them up, you short them out, your contacts could weld together, and then you've lost an output.
So that output right there is gonna be a physical output, that motor right there.
Yeah, this would be just a load that we're going to use one of our output ports on. I mean, it could be a light bulb. So this is what we have down there. And it depends on what they run out. What do they use for the common, for the loads? So what do they use for a common? This would represent my output port. Right? You understand that? So if I hook a source out to the load for one of my output modules, then my output module has got to sync. Right? You understand that? So if we use syncing uses a negative common on DC, sourcing uses a positive common. Common is just we gotta have two wires. So over here, these push buttons are using a positive common. Right? And what's that positive voltage looking for? Well, it's looking for a negative common, right? You understand that? So what we do on our input, my input would have, so a sourcing input would have to go to a what? A sourcing input device would have to go to a sinking input. Y'all understand that?
Sourcing is a positive,
Common,
and sinking is the
negative common. Because here we're dealing with DC. What about sourcing and sinking on AC?
don't matter.
Don't matter, because sourcing doesn't have a sign. But here we're going to be dealing with transistors, we're going to be dealing with digital devices, electronic devices, and those suckers operate off of DC. If you give them the wrong polarity, you could damage them, but most of the time they just don't work. So that means if I took a sinking device and hooked it up to a sinking input, the switch won't work. But it wouldn't hurt anything. So if you look at the MicroLogic, if you look at the SL, the SLC 500, SLC 504s down there, you see the input module says, anybody on says what? Sinking. So that means if I was to wire up those inputs, on my inputs I would use a positive common, right? You understand? And that I don't have an option on what I use for the common for the inputs because it is a sinking module, right? You understand? I think the output is sourcing on the 500, on the 504. So if you're on the 504s, just look at those modules. We have a 16-bit input module, and we have a 16-bit output module, I think, on most of it.
How do you determine what module you have?
It depends on I don't know.
Like, you were looking at those to see if they were syncing.
It says right on the front. Every modular PLC I've ever dealt with, it's on the front. You don't have to open up a door or anything. So normally to get the actual model number of the input, you gotta open up the door, right? But the syncing and sourcing is actually on the front of the module.
And when we've been configuring it, you see it's saying syncing input. It says syncing like voltage DC or something like that. When we was configuring the model, a lot of times when we choose the model, it tells us what it's syncing.
Yeah, should on the list y'all hear what Vincent said? When you go in and when you create a new program, on a modular PLC, what do you have to specify? You not only have to specify the processor, you have to specify what type of module you have in each slot of that rack, right? You understand? It should be on that too. But like I said, every module I've ever seen, it specifies inputs or outputs. It specifies whether it's syncing or sourcing. Your fixed PLCs is where you're going to have to actually probably look it up in the data sheet. So if we look at the 1100, it's got two commons for your input. And it's up to you to set them up as what? Syncing or sourcing. But they're groups, I can't remember what groups are. And it's also that on 1100. 1100, it's okay if you pop the cover on your inputs. You can see those two commons, and you can see how, I don't know to put those trainers together. You can actually see how they're jumped. I think they use that. I can't remember what they use. We got 120 volts on the output, 120 volt low energy. So if you want to open up and look at the outputs, you need to put on safety valve. If you're going to make measurements on the outputs, you need to have insulated gloves, right? The 504s, it's 24 in, 24 out. So. Everybody okay on the data file? Open the data file dialog box to monitor the operation of this shift right and this shift left. Reset the shift bit left or bit right. Instruction to back to the starting. Okay, skipped over that. So here's our logic.
Logic set. Here. Nope. Logic Pro. No, this is RS Links. Thanks. Looks like I might have closed it out. That says it. Dang it. So we'll open up a new file on this, and this is a MicroLogic. I need to look it up. 1100. I'm pretty sure it's a B. Okay. That's one thing nice about fixed PLCs is that you don't have to specify the ports, right? So we're going to put in let's find our logic up here. There's our logic. And notice we got what? And, or, and clear. Does the book cover the clear? You need to put that, add that. What would y'all think the clear would do?
It all out.
Clear the information out. But does it?
Yeah, what we can do with the clear is we can set a register to zeros before we use them. No, it's real easy.
Whatever it puts in, outside the office. Send it to that destination.
I can't get this to insert a run, guys. What am I doing wrong?
Highlight on the left side.
Oh, okay, gotcha. Then we'll come in and look at our logic instructions. And we'll look at a NOT. It looks like it. I might have got that wrong.
You don't like it.
So it is an output. How would you? Let's look at this. Let's just for the heck of it. Yeah, but it would do that. It would do that on anything, but it still gave me an error. So this is my error. So when I come over here and I need to change my PowerPoint.
Put in a V-rest where we can see it then. Not like that.
Oh, so still let me tell me that. So they're using V3 in the book. What are they using?
0, 0, and 1.
Of course, these are going to be words, right? Okay, so that cleared it up. So you notice by default, it gives us our number in what base? That's not it. Binary. But by default, it gives us our word in binary. Micrologic, we let you get by with that. Putting, putting two outputs in, series. This won't let you put them in there, so you gotta put your down drop in there before you can, looks like it. So source. Source, what can the source be? Where can it come from?
Arrest.
Or a number. What we're gonna get here is give you out the address and mode supported by Allen Bradley. So we can use immediate addressing here. What's immediate addressing? So immediate addressing, the operand is part of the instruction. Y'all understand that? Now the destination has got to be a what? It's got to be a register. Are we okay?
Yeah.
Okay. And then this move right here, we would, the source. We're going to use this with other instructions. Right now, we don't have to. So what I'm doing now has nothing to do with the NOT, because the NOT only works on one byte, right? So on the NOT, what we'll do is we'll either use the integer 7 or 0 or 1 for the instruction.
You put the,
Huh?
Yeah.
So here we'll get this from N7 colon 0. Okay. So what do we need to do? We need to download this, right? Oh. Oh yeah, that's clear mode. Full screen. File 2, rung 0.
hey,
Oh. I got binary on my mind. I got hex on my mind.
that's why I was gonna ask you what the name is.
Yeah, I think it's, oops. Let's see if it takes that. There we go. Y'all see what I just said? Y'all understand what's happening? Yes or no? Your move instructions does not deal.
Run two, that'd be the second move.
It said A.
They said your problem with the A.
It wasn't with the 5s.
If you hit the error check, the thing will come back up.
The problem is your move instruction does not deal with, it deals with numbers, base 10 numbers, it deals with decimal numbers. Okay, you understand that? So when I entered AAAA there, it didn't know what to do with AAAA, right? Because that is not a number. So what I did is I put an H after the AAAA. It gave me what? The actual number that it represents, decimal number that it represents. Now AAAA would have the most significant bit set, so it's interpreted as what? The
which has nothing to do with logic. Signed numbers have nothing to do with logic.
So let's upload it now, or download it. Okay, so we're going to take N70, which is the all fives, and can you see what it did? It converted them to all A's, right? So 5 would be 0, 1, the 1, 0, 1, 0, 1, 0, 1, 0. So what it did is took the output and the what on it? A knob. So your logic, I need to go back and retrace it. Your logic is an output instruction. So if I was going to do a NAND, I would have to do it with 2 runs. Right? You understand that? How many outputs can we have per line? 1. Or per line, not per run. How many outputs can we have per run? That's in parallel. So in the motor control, there's no such thing as series parallel circuits. They're all one. There could be a single series device, right? You understand? Or parallel. What determines if a circuit is series or what? Now your L1 and L2 see the series parallel circuit. That's what a lot of people don't understand. Series parallel circuit. But a run can either be a single element or a single output or a parallel circuit. Okay, y'all guys take a question.
And
I'll tell you, this is a no. We use the term any and we use the term all. We're talking about and all, right? Or Nancy knows.
input 1, 1, 1, I'm not doing
What are you not doing?
only input we got over there is 1, 5, 1, 5.
What do you mean? This is an input. This is an input. We're bringing in the whole input. So we're bringing in input module 1. And how many bits? I'm not specifying a slash up here. So I'm taking input module 1, not slash anything. So since I don't put a slash, we're designating that as the entire 16 bits. Okay. So here I'm getting a 1. If I look at the registers, on this one, by the way, you can hit this up here. You can't do that. And what we're doing is we're looking at my outputs. But now let's go back and look at my inputs. Okay.
Hit 1 to 3s at the same time. Input 3. No, I'm talking about, see, you. Okay.
We're not using 3 for our NOT. We can't use 3. NOT only works with 1/16-bit word. We went ahead and put those 2 moves, so when we start dealing with our logic, I have two operands that I'm bringing in to AND together or together, right? When we do a NOT, how many operands are we dealing with? 1. Okay. So I'm getting my operand from which input?
1.
N70, which is coming from input 1.
Right.
Okay. Right, you understand?
Yeah.
Okay.
Insert 1 is not being used.
What's that?
Insert 1 is not being used.
Well, it is. It's just that, yeah, we're not using it later on. Yeah. So these guys are sourcing, right? You understand? So now I'm bringing the 0 in. Well, these guys here are what? What's this comment over here? So let's look at 5. 6. we'll come over here on 6, and it's giving me a 1. Oh, so what are those guys hooked up for? Syncing for?
We got power on it.
Well, what does it provide me when it's closed? Does it provide me a ground or common, or does it provide me a 1, or does it give me a 0? Okay. So what are they hooked up, syncing or for? If they was hooked up sourcing, I would get a 1 from them. Y'all understand? Yes or no? Y'all having a problem with that? This is the one I have open. Of course, I erased all that. If they are sourcing, if I press the button, I get a 1. If they are syncing, I press the button, I get a 0. Okay, y'all understand that? So what am I getting back? I'm getting a 0 when the switch is closed. So that means these inputs are hooked up. These are syncing devices. So my port is going to be, I have to look it up for sourcing, right? Y'all understand it? And you can't change that. I don't think you can change that on MicroLogic. So switch 6 is closed. It's giving me a what back? 0.
Switch 6 is open. It's open, but it's in it as a 1.
Okay, so I said that wrong. I thought it was closed. So it, yeah, so I had my hand over there. So let's go back and rephrase it. So when the switch closed, I have a what? 1. So maybe that's why you're so confused. So if it's closed, I get a 1. So what's it hooked up for? Sourcing. What we're doing is, if it gives me a 0 when it's closed, it's hooked up syncing, right? You understand? If I get a 1 when it's closed, it's hooked up. Now let's look at our outputs. When we look at our outputs, so what output are we using? Output 2. So I'm going to open this switch up. Okay, so what do we get from that now? Okay, so let's open it up. We get a what? 0. When I look at my outputs, yeah, that's good. But the output, this is what we're trying to do. When I get a 1 on the input, I would get a 0 on the output. If I got a 0 on the input, I get a 1 on it. Do y'all understand why? From the knob. Looks like the Allen Bradley actually displays binary down here. Where Logic Pro, the guy displays what? Yeah, well, decimal. And there you can see, so this is interpreted as a negative number. Right? Understand that? Now, if you don't understand 2's complement, you can't do that 1, 2, 4, 8, 16, 32 always, because that does not work. Because this is what we call a 2's complement number. It represents a negative number. So since this bit right here is set, then it interprets it as a what? I mean, this is what gets people confused. So they try to deal with binary. So this is a -1. This is supposed to be a -1. I don't know if I can do this on my calculator or not. The Logic Pro had some problems
like I do.
We all
So what I'm gonna do is I'm gonna come over here and put my calculator on programmer's calculator. And what I'm gonna do is, so right now we got it on decimal. I'm going to do a -1. And then I'm gonna do it in binary. So that's a -1.
All no more. That's
Yeah.
double word.
This is more than a double word. This is my calculator. This is a Windows calculator. This got a huge resolution.
Quad.
I think it's probably more than quad. Might be more than 32. It might be 64. Since this is a 64-bit processor. So if I'm gonna go back to decimal and do a -2. Oops. And then I'm gonna come up here and put this in binary. And notice the 0 bit is clear. So I don't know what this guy.
Oh, it says quad word on it, Rich.
Oh, it does.
Put it back up. See it right there, lower left quad word.
Oh, okay, yeah, quad word. So this is a double quad word with accordion. Of course, the Allen Bradley PLCs only deals with what Windows Scope refers to as a double word, which is what which Allen Bradley calls a long word, which is 32 words. So this is the actual number we have. And this guy's giving it as minus this, but that's not exactly right. That's actually -1. But what we're not looking at the way, and this might be why if we did this on Allen Bradley, what do they show on the knot? Yeah. So what Allen Bradley does is it shows you the actual binary number. Of course, what I did is I put AAA in one and this on the other. We don't have enough inputs to support this on the little micrologic to get you that, but it's still running. Like I said, Logic Pro is a really, really neat application. It lets you get by and don't do everything exactly right. I'll show you all another problem I've had with it. Telling it to convert from decimal over to BCD. I don't like to do that either. But whatever I put over here, so here I'm putting zeros in, right? Y'all understand that? And what does my not give me? Yeah, it gives me a 1 or integer. We can't look at both of them at the same time, I don't think. Let's see if, no. So all you can do, of course, if I was on the Allen Bradley PLC, where would I look at these data files at?
in the tree.
Down in the tree. And what can you do? Just click on any of them, right? You understand? And then on Allen Bradley, you go through your data files over here on the left. This would take a little while, but we could come in and we could put a jump instruction. And you see these signs all the time out there that's running off PLCs where you got a bunch of lights and one light goes off and the other one comes on. And just, this usually uses this knot. Y'all know what I'm talking about? Yes or no? And you see some of these, there's a lot of PLCs stuff that has been, there's a lot of stuff, especially these little small PLCs that don't cost that much money. Used to you'd have these signs on the side of the road and it might have a big arrow up on top of it and it'll show
you know, it looks like the lights are going in sequence, it looks like it's pointing to it. A lot of times on marquees, you'll have the lights blink alternate from each other. We'll show y'all the bit shift is what we can use to implement the lights that appear to be in motion. This guy right here, we could do this to make the lights blink. So what I could do is I could come in here and do a jump instruction, right? You understand what I'm saying? So where's my jumps at? Let's see. I think we got jumps available on this. Hopefully. So there's our program control. Oops. And Logic Pro will let you get by with putting instructions in your end, by the way. So we're going to jump it. Let's jump it back up above the knot. So I'm going to put a label right here. Oops. Okay, guys, what's required for a jump instruction? But the label is considered to be what type of instruction? Input. And the jump is considered to be a output. So what do we need to put on the right over here? So it labeled this Q2. So Q2 is the file we use for our jump instruction. Not O, Q2. So it automatically stuck that in there for me. Oops.
Aren't you supposed to have that label above the jump?
Yes, I am.
Above the knot.
I just inserted it in the wrong place. We're not using any of our bit files, are we? Of course, what probably else do I need? So right now, if we came up here and ran it, we probably wouldn't be able to see it because everything's happening so fast. So we probably need to put a little time delay in here, right? And probably add some more logic to this. It's going to take a little while longer. So this is not, I'm not, we're going to take up more time in here than I want to do. So what I could do here is what?
Use the sort.
Yeah, so I can come up there and get that thing up there, right? Put in a number to start off with. And then every time we could do what? Yeah, and then have a timer set up to give us a certain delay. Okay, and then do what? And of course, we can make the lights basically flashing almost in pattern. There will be a little more to this than. So if you ever get on the side, you see these signs up on a building or something, and they're flashing in sequence or stuff like that, then this could be done with a dot. Or maybe, again, we could set this up if we worked on it long enough so we could actually load the pattern that we wanted it to flash in, right? Understand? Yes or no?
Move the status.
Huh?
Move the status.
Status register.
Could I do what with the status register?
And the blink flash.
The S bit, I guess that's what I'm talking about.
Oh, you mean to give us a time? You was thinking about the time base that we can use. We could do that. But here I'm just trying to do a delay, right? If I'm just going to do a delay, I'll probably just use a timer. If I wanted it to blink 3 times or 4 times or something like that, then I would probably combine it with one of those timing bits, like we did on the bell.
So I wanted the bell to ring how many times? But then we combine that with a count. Here, if we just want it to blink all the time, all we're trying to do is set up something so I can do what? I can see it change. I give it enough time for somebody to see. Some of y'all have done that in there, where you turn on a light, but then you don't have any type of delay at all. And you say, well, the light's not coming on, right? This has happened more than once. Well, the problem is,
Going by so fast.
yeah, it's going so fast. The dang thing's flashing so fast that you just don't ever see it.
What is the significance in the label instruction on, 1-1? What is the,
Well, what we're trying to do is we're trying to make the program loop.
okay, but what is the B3 output on the label?
Well, the label is an input instruction. You gotta have a coil.
Okay, what is it?
Can go anywhere.
It's a B3, it's an internal coil. I mean,
So it's just out.
yeah, it's just out there. You gotta put some type, yeah, the label is considered to be an input instruction. And we have this and this guy have to have the same label.
Right.
So we label it with Q2 something, right? You understand? So literally we could have inside a rung, inside a ladder, we could have up to 256 jumps for micrologic, for logic product. I mean, not logic product. RS logic. So we gotta put something over here. Right. But it could literally be any output instruction. But, so you could put something up there. In fact, I could probably take this and do what? Well, I could probably add this and put it there. And that would reduce the run because this is an output. So every time you jump to this label, it would do the nod. Right?
So what you're saying, you could just put the label inside a wrong too?
Put that.
Or move this in, yeah, so I could put the label in this run right here and go away with it. Because every time,
Okay. That's what you were just saying. You could have did, that step could have been omitted.
yeah, this could have been it. We could move the label down in here, and then every time the label came through, we would nod it, right?
But, wait a minute. When we hit Q2, we're gonna jump over the knot and the TON in the timer.
So this is one way we could have done it right there. We're not gonna jump over the nod because the nod is in the label wrong.
Right. We want to go back to this.
So every time it hits this label, it's gonna go back up here. Take this through, it energizes this and come through. Of course, the timer right there don't make any difference right now. What we need to do is delay it before it got to the jump, right?
Put a John bit.
We could, and then that way, we put a done bit instead of the jump, then, it would cycle through, it would come back up here and keep monitoring our inputs, until,
Let's do that, and let's see what it looks like.
nah, we gotta move on. Sorry. We gotta move on.
That's why I got Logic Pro and I got it.
Yeah, but be careful with Logic Pro. It lets you get by with some stuff that we can't do, right? So the first thing we're going to look at, that we looked at was the nod instruction. All right. So here they're doing a nod. They're doing a what? And then or and an or. So what we'll do is we'll bring in this one, and all we'll do is put an instruction up there where we can load all this stuff. So let's go to Logic Pro, and then what we'll do is we'll come back here and open. I'm gonna go to Docs. You book, and what's this figure? Oops. Do that every time. And then all we need to do now is, we'll see what they do. Now notice, come on. So what inputs we're using? We're using input 1, N7:0. Which one are they using? They're using bits. So they're using B3:0. That way I won't have to change all of those. And then but I think 3 is the next input that we have available. And then
So you gotta use B3 column 0 and B3 column 10.
oh crap. Okay. Oh, I see what they're doing.
They're not running into each other.
They're not, but I'm trying to get the same. I'm trying to use the same two numbers, so that way I don't have to. We can input on the switch and output on here.
I hate it.
I'm just using output. I mean, you can use these integer registers if you want to. Odds are, if we come in and use one of our bit registers, so instead of using the integer register, how many instructions do we have? If we use an integer register, it's going to interpret it as a signed number, right? You understand that?
Using B30 and B13.
So here we're using 0 and, well, we can use 1. Okay. And then here, let's save them in our other upper registers. How many we got? I don't think Logic Pro supports B10. We'll try it. Yeah, so Logic Pro doesn't support the B10 register. So we'll use B10 or B3. Let's use 10. No, this is going to be, I'm sorry. This is going to be 0. Okay. And then we'll save it in the colon 10. What I'm trying to do is use the same numbers for everything. And so what we're doing is we're changing the output. So this will be 11. And then this right here will be B colon 12, right? You understand what I'm doing? We're using the same bits as our inputs, all except for the not. And that's probably my problem a while ago. When I saved it in an integer register, my not interpreted it being an integer, so it gave me a negative sign. That was probably my problem. So let's check this out. So I'm getting my two numbers. I'm getting one of my number from B3, one of my operands from B3 colon 0. The other one I'm getting it from B3 colon 1, which I think that's wrong too. Colon 2. Input 3. That's right. So I'm getting one of mine from input 1, so I'm getting it from these 16 bits right here. My other one, I'm getting it from input 3, which is these 16 right here. Then I'm taking them and storing them in B0 and B1. Okay. So here I'm gonna not whatever's in B0, and I'm gonna put that in B10. I'm gonna and B0 and B1, and I'm gonna put that in B311. Then I'm gonna OR B0 and B1 and put that in. I need to put this in 12. I'm duplicating. And this guy here needs to be 13. Okay, so let's go and upload it. Or download it. Put it in right.
So this in the book?
What? Sorta. But the one in the book doesn't tell me. So what I would have to do is I would have to preload some registers. Okay, which ones are they using in the book? They're using B30 and B31. So what we're doing is we're ORing. So I would have to go in and literally to see this work is I would have to load all these B3s with. I'd have to load B3 with something. I'd have to load B2 with something. I'd have to load B5 with something. I'd have to load B8 with something. Right? You understand? Okay. The way we set it up, or the way I set it up, I'm going to bring my input in from two move instructions, and then I'm going to not one. I'm going to and the same two numbers. I'm going to OR the same two numbers. Okay, so y'all understand? So is it in the book? Sorta, but we modified what was in the book a little bit so we could do the same numbers. So this is the not, and this guy's not displaying. Okay. Now look at what our ORs do. So what would be an application of an AND? Of course, I don't know what was the exclusive OR in there too.
No.
Did I set that up?
When they do, they use exclusive. They use as a four instruction, not and.
Okay.
Or.
So these are our four basic instructions that's available to us: not, and, or, and, should. So notice here, if we look at the lights, no, that's what I should. We don't have enough lights. So I'm taking what? 7.
7.
Right?
Destination.
And they were not that. I don't know. We need to probably look and see if there's a way we can make logic code display binary. Which would be the way that we want to see it, right? So if I AND these two numbers, so what numbers do I? What would be an application? So let's say I come up here and I'm ANDing two numbers, and what two numbers am I ANDing? Oops. 1, 2, 3, 4. Oh, no, still one more. We're doing groups of 4. I'm trying to do groups of 4. Let me erase it. I messed up.
These
Left or right?
when you write numbers, I write numbers like I write decimal numbers. So if I'm gonna write 3,033, I don't go from right to left, I go from left to right. But when we number the bits, they go from right to left. But when we write numbers, we usually write numbers what? Left to right. And what we do is we just go, if we're gonna do binary, and we're doing, then I would go in groups of 4. And that would be 16 directions. And right now I'm adding it with this right here. Okay, so what's 1 and 0? What's 1 and 0?
0.
Okay. What's 1 and 0? Okay. So right now what I would end up with is, if I look at my AND operation, I should have a what? 0. Because AND is both, all. So both these have to be 1s to get a 1 in my output. Now if this is an OR, my OR should show me a 7, right? You understand? My exclusive NOR, exclusive OR, so we should get a 1 if they're not equal. So what would I have here? So I should have a 7 results on my exclusive OR too, right? Okay, you understand that? Huh? Would be the opposite, yeah. So that means if I look at my knot, so I'm knotting this right here. If I was looking at my knot, I would come up and see this, right? If it showed us binary, which it don't. Right? This is what our knot gives us. Of course, what it's going to do is it's going to give us a negative number. And it looks like it's doing this right. A Logic Pro looks like does decimal on everything. So my knot, I got a -8 to be right. So that's right. A while ago it displayed it wrong. What was the little trick I showed y'all you could do to do the 2's complement? Y'all remember? Invert everything past the first one. So this is a negative number. How do I know it's negative? So that's a 1. And what we do to go is I invert everything after the first one. And then I would invert everything after the first one. And this would be that this number right here is representing a -8. Okay. So that's a little trick. So you can go from a negative number to a positive number by inverting everything to the left of the first one. So this is what's actually in the register, but it displays it as a -8. So that's right. I don't know why I did it. -1 is a 655 while ago. So my knot gives me a -8. So it didn't do it in binary. My AND gave me a what? 0. My OR should give me a 7. And my exclusive OR right now is giving me a what? But what we should be able to do now, so if I come up here and close this one, this didn't change the knot because we're knotting this one right here. But my AND went to a 1. Why? Well, if we come back and look at these two numbers now, what I've done is I've changed this bit right here over here to a what? To a 1. Which means my knot is going to be the same, right? Y'all understand? My OR is going to be the same. So my AND, what do I have here now? Yeah, I got all 1s. Oops. So this will be my what? This will be my and. What will my or be? Same thing. Oh, yeah, okay, this will be my or, right? What would be my exclusive or?
One, zero, zero, zero.
What's that?
1, 0, 0, 0.
Now here they're the same. So here we get a 1 if they're not equal.
0, 1, 0, 1, 0.
There you go. So my and should go to a 1. My or is still going to be a 7. And my exclusive or should show a 6 now, right? So my and went to a, this stayed the same. My and went to a what? 1. My or stayed the same. And my exclusive or went to a 6. Now what would we use an and for? So I'm dealing with a whole 16-bit word. So any application for an and?
Application for that.
Yeah, but what would I apply that to? I know what it does, but what would I apply that to? Now we got some registers that go along. I mean, we got the flag register to go along with it. So let's say I've got a 16-bit. I'm bringing in a 16-bit input, and you can understand. So now what I can do, instead of playing around with my inputs, instead of bringing in one little bit at a time, right? You understand? What can I do? Well, I can load an entire 16-bit input port at one time. And then I need to start figuring out what's going on with those bits. I can treat them as a number. I can treat them as an integer, right? You understand that? So what we're doing here is actually kind of treating these like numbers. Well, let's say I bring in a 16-bit input. This is just what I'm trying to, I've seen it applied to. And I want to see if this bit right here is a 1 or a 0. How can I do that? So that would be this bit 0, 1, 2, 3, 4, 5, 6. I'm trying to see if bit 6 is set to a 0 or a 1. Well, what we can do is we use what we call a mask. A mask is when we cover things up, right? Understand that? It's just like when you put on a mask, what do? You cover up your face, right? We have two types of masks. We have what we call an and mask and an or mask. What I do with an and mask is I use it to determine if a certain bit or bits are set. So what I would do is I would come over here and I would and mask this with, so this would be my and mask. And we use this so much, there's a move with mask instruction, by the way. I think it's a mask. So this would be my mask. So what we're going to do is we're going to come up here. If I and these, what would I come up and give me? This would give right now. Give me a what? 0, 0, 0, 0, 0, 0, 0, 0, 0. Right now, this would be a what? And I would get this. Now, if I check this number to see if it's equals to 0,
then if it's equal to 0, it meant that this bit right here is what? A 0.
Let's say if we loaded in again and this bit right here came up to be a 1, then my answer would no longer be a 0, right? You understand?
So what we can do is we can and mask it. And what we can do is we can use the answer to check to see if a bit are equal to 1 or 0. Because what we're doing is we're stripping off all the other bits. We can use it to clear a bit. Let's say I wanted to clear this bit right here. No matter what it was, I always wanted it to be clear for some reason. Then I could put a 1 in my mask.
So we can use the AND mask to see if a input or a bit is a 1 or a 0. Or we can use an AND mask to always clear a bit. We can't use it to set a bit, but we can use it to always clear a bit. So if I come over here and use this AND mask, then this would come through. So if this was a 0, it would be, so right now this would be a what? This would be a 1. Well, this is a 1. This would be a what? A 0. Well, that's a 0. This would be a 1. This would be a 1. This would be a 0. What if this was a 1? Well, it don't make any difference. If this is set in a 0 in my AND mask, no matter what that bit was, I could always make sure that that bit was reset. Right? You understand? And of course, the rest of them would come through unaffected.
So in my original number, no matter what this bit right here is, it will always come through as a 0, right? So with an AND mask, we can use it to check a bit to see if it's set or cleared. Or we can use it to do what? Make sure a bit is always clear. Or false, or whatever you want to say.
Repeat that one more time.
No, I can do that. We got two
Said
functions.
it clear is the same as 1 and 0? You
Yeah,
had
1
said
and
at first, you said see if a bit is 1 or 0, which is on or off. Okay. And then you just said it's set, if the set are clear.
What would you think?
So that's the same thing.
Same thing. What we're doing, or I could just say true and false, right? What's nice about digital is that most of the time digital only has 2 steps. So we can use a lot of terms to represent those 2 steps, right? What are some of the terms we can use? We can use 0, 1, true, false, set or cleared, on and off. So you have to get used to the programming language that we're dealing in. This might be the input is energized or not energized, or where we're getting this information from. So in AND mask, what can we do? We can use it to clear bits.
Set bits.
We can use it not to set bits. We can't use this to set a bit, but we can use it to clear a bit, right? We can use it to see if a bit is set or a individual bit is set or cleared. So what I want to do, if I wanted to check to see if a bit was set or cleared, I would come up here and I would use all zeros. The one I wanted to check on, I would use a what? A 1. We'd use that as a mask. If I wanted to clear a bit or clear bits, then I can just put a 0 in my mask. Don't understand the mask. You got to understand that right away. And this will make later. I think that's covered in this chapter. But we have a move with mask instruction. So what that means is we can literally combine a move instruction with an, I'm pretty sure it's an AND mask. Huh?
yeah, this is I think this is even supported by Logic Pro. I know it's supported by Allen Bradley. We'll look at we'll look at our move instructions. Yeah, so look, we have a move. Everybody's okay with the move instruction? So the one next to it? Move with MWM. That's a move with a mask. So what we can do is we can mask off some of the bits. So what can we do with the exclusive OR? Well, exclusive OR, I can set bits. No matter what they are, I can set bits. And I wish it showed us binary, guys. So here's one of my numbers, right, for my AND. You know, let's say, so right now, let me upload it. Or switch it back into run. I don't have to upload it. Don't look like it's doing that.
Can we take 5 breaks?
Yes, we can. He'll take a break. Take 10, Seth.
I'm working on the picture.
Tommy grabs it, bites his brains out, keep on walking.
That's out.
You wanna see that? Tommy
It's that
walk up on
time.
you, bite his brains out, and then keep on walking. I tell you another one I don't like, that he will.
Yeah, there's a lot of things that Logic Pro gets messed up on. We might, I might put this into the RS Logic. So what I was going to do is if my results came up to be 0, I was going to turn on an output. If it was not 0, I was going to turn it on. But I have to figure this out. I don't know if I'm doing something wrong or not. It looks okay to me. So primary, the AND mask is used to strip off to make sure bits are cleared. We can also use it to determine if a bit is set or cleared, right? The OR mask, both things use the OR, an OR mask for. ORs and ANDs are basically opposite of each other. So ANDs, I say all. So here we're only dealing with 2 bits at a time. Okay, you understand that? So we say all. And when we say OR, we use the term what? Any. So if we use an AND to make sure that certain bits are cleared or a 0, what would we use an OR for?
Make sure it's set.
Make sure they're set. Or a 1, whatever one you want to call it. What I was trying to do, I think it's our next slide. We'll go ahead and look at it as soon as I find the right slide.
You said all, you say all.
Yeah, those are just general ways that we teach them, try to show you what the difference between OR and AND was. So AND, we use the term all. Yeah. So it's just like when you come up here and you start wiring contacts. Okay, I'll start wiring contacts. And we get assigned number to these contacts. And then I come over here and I put a coil. What would you say about that, Al? You say all, as soon as you say all, you know that these are wired in one. And they're wired in AND. You're right, they are in series, but what we're doing is logic. Now, if I come over here and start putting contacts in parallel, that's an OR, but what we use the term any. So if any one of those contacts are closed, then we say it's an OR, right? You understand? So just saying what the contacts do can almost tell you if it's a what, an AND or OR. ANDs and ORs are what's required to energize the load. NANDs, NOTs, and ORs are what's required to de-energize. So the problem is people will look at contacts in series and it's AND. But that's not true. Because I could just come back and do the same thing. And this happens every class I ever teach. They'll see these contacts in series, right? And they'll say AND. Our contacts in series are AND. But that's not AND. Because what this is going to do is that these on the top, it takes all of these to turn this load on.
Right.
Your NANDs and your NOTs are what's required to turn the load off. Okay? So I would come over here and I'd say, okay, what will turn that contact off? Well, any one of those contacts. Any one of those contacts would turn it off. So this is a NOR. So NOTs and NANDs are what's used, ANDs and ORs are what's used to energize our load. NOTs and NANDs is what we use to de-energize the load. It's true when it's de-energized, right? You understand? So I come over there, and now every class I've ever taught, and this is one of the, it's almost as bad as examine on and examine off. So it would take all of these contacts would have to be open. Over here we say all of them would have to be closed. Over here we say all of them would have to be open to turn the load off. Right? You understand? So this is NAND. And that's the way I try to teach it. Even in motor controls. When you start doing the logic. Of course, when we do it with contacts, we can do it with a number of contacts, right? When we do it with logic, then we're only working with 2 bits at a time. So I'm ANDing 2 bits of a 16-bit word, right? Okay. What if I needed to AND? What if I needed to OR 3 16-bits? What if I needed to OR 3 16-bits? So let's say I had 3 16-bit words that I wanted to OR. So I'm trying to OR it using the commands we're working on now, not contacts. I'm trying to OR. Okay, let's just do forward. So let me do in 16 bits. Let's say I wanted to OR this, and I wanted to OR it with that, and I wanted to OR it with this. Well, if I did that, this would be a 1, this would be a 1, this would be a 1. Right? Okay. Well, how would I do it with OR instructions? Well, I would take these 2 right here, and I would have 1 OR instruction, and then I would OR it with this. And that would give me this, right? And then what would I do? Then I'd take, yeah, you're exactly right. I'd take the results of that and OR it again, and then I would come up with my final answer. So what we do with these OR instructions, if I wanted to OR 3 numbers, I would OR 2, right? You understand that? And I might put this in B30, and then down here I would OR it again. So literally we can OR as many numbers as we want to OR. We can AND as many numbers as I wanted to AND, right? You understand? So we would we would keep doing ANDs. So if I needed to AND 3 input ports to see what was going on, then I could do what? Then I could do, 2. Exclusive ORs don't count for exclusive ORs. Exclusive ORs is always 2 bits, or exclusive NORs. ANDs and ORs. So when I'm wiring contacts, how many contacts can I hook in AND? Yeah, I hook a lot, right? How many contacts can I hook in OR? As I want. How many contacts can I know, or how many can I NAND? A lot, right? You understand that? So we need to have the ability to do that with an instruction. But if we do contacts, we're only working on 1 bit at a time, right? You understand? When we do these ANDs and ORs and NANDs and NORs, we're working on words. So I could come in, I could load in a 16-bit input port and OR it with something, or AND it with something, or exclusive OR it with something, and then use that results to make a decision. So what I was trying to do over here on my RS Logic was come up with a program that says, okay, why would I want to AND? Well, what we can do is we can set up a mask, and we can determine if that 1 bit inside that mask is set or clear by ANDing it with a mask. But the sign bit's, the 0 bit's not working. So notice so my AND is picking it up. See, so it goes from a 0 to 32. So that means bit 7 would be set, right? So what should happen is when I'm sitting, if the thing was working right, then right now it says, okay, it's not 0. So right now this should be off. I'm sorry, it is 0, so this should be what? You see what I'm checking?
Status bit.
Checking status bit to 0, 2, which is the 0 button. So something's going on. But this is RS Logic. What am I trying to do? Set it up on the Logic, not RS Logic. This is Logic Scroll.
So you actually don't know what in that source A, where you taking that whole
Well, you do and you don't. If you do binary, you know that this is the FFFF. Problem is we can't make this guy display anything but decimal. And I'm pretty sure in the Allen Bradley software, I'm almost sure we can display different bases, but I'd have to go back and look that up. But this status bit is not working. So these are the bits that we have available to us. I think this is covered on the next slide anyway. Oops. I gave y'all the thing on the addressing mode, right? So these are our flags. And what does a flag do?
I got so much in my head, I can't remember.
Let's know something.
Let you know that something happened, right? So if what they check for is true, then it'll be set. If what they set for is false, then it'll be clear. These are the same flags that we would use for our math. About the only thing that we would probably be concerned with. We can't cause a carry, we won't cause an overflow. So the two things that I might want to look for on the logic is either if my results was what? 0, or if it's a negative or positive 1. So the sign bit, all it does is just follow the most significant bit. That's all it does. If it's a 1, it'll be a 1. If it's a 0, it'll be a 0. So that really wasn't telling me much. But when we use an AND mask, most of the time what we're looking for is if the results
came up to be 0, it would mean that that bit that I'm checking would be cleared, right? You understand, or 0. If it came up to be a 1, it would mean the bit I'm trying to check for is a 1. Yeah. Or say it. Of course, it's not working in Logic Pro. So what I did is I got rid of everything. When I first did it, I thought it might be getting confused about which operation that it was using.
Logic Pro or Harmony?
Logic Pro. What did I say?
You said Logic Pro, that's how you go to
Yeah, so notice RS Logic displays a nod in binary. Just for a minute. Logic Pro looks like it's going to display everything in decimal, which makes it a little harder to teach this. So what I'm doing is I'm moving 2 numbers into my 2 registers. I'm adding B0 and B1. And right now I'm checking to see if, so if I wanted to check to see if bit 6 was set, well, what I would do is this right here would be my mask. So bit 6 is not set or not 1, and what's it giving me back? My AND's giving me back a what? 0. And now it is set, right? That makes sense.
Okay. Oh.
Now what should be happening right now, this output should not be working, and right now this output should have came true, right? Go ahead.
Isn't that supposed to say S2:O/2?
Yes. But normally we've only got 1 status register. So watch what happens. I'm gonna take this off. I'm not sure if Allen Bradley does this or not. But what I'm gonna do is I'm gonna go what?
S2:O/2.
2 colon 0 / and we're looking at the carry. We want to look at the Z flag, so it'd be 2. Okay. Now watch what happens.
Oh, change.
It's just like when we want to use the actual time base is in the status register, and what's the time base? Oops. S2/4. But did y'all notice what it put in there when you put that? So I'm going to access the stat. I'm going to access that. It's not going to make any difference. Put it back to program. So what I'm saying, Logic Pro drops a 2, but it's still right. So I can come up here and, okay, so I can come up here and what's the time base? S2, 0, 4. Oops, didn't like that, did it?
It's 4.
No, it's S2, 0/4. That's the actual true address. But Logic Pro, what it does, is what? Drops the 2.
Oh, we don't love it.
Yeah, we can look and see what Allen Bradley does. It's the same bit.
Putting that timing bit in there, you want it series with that label?
No, I was just going to show y'all address it. Understand?
Oh, okay.
Yeah, I was just going to show you what it is when the address. So when I come up here and look at the status register. Okay, so these are all the S2 registers, right? And notice what Allen Bradley calls it. SM cover 4. Right. But it's actually S2, right? Y'all understand that? Yes or no? Yeah, I'm gonna come up. Here's my S2 register.
Yeah, it's an S2.
But a lot of times, so it looks like Allen Bradley does the same thing, and he drops the what? 2. Is that a big deal? No.
Cause it did it automatically. So, all I wanted to show you, Larry, was that that's the way we would address those status bits. So, you're right, it won't do much, but when I put it in run, so what, it don't look like that's working either. So it is 0, no, I'm doing the wrong thing, sorry. So what register is that? What register is the timing bit? I'm using the wrong address. No, it's not 0. That's my problem. I got confused with it. So here's the status. Here's the, so it's 4. Yeah, then we choose a bit. No, this is the time base.
Oh,
This is the 0 flag. Okay. So no, I don't need to change that. The 0 flag is at it's in the S2 register, and what bit is it? Bit 2. Word 0, bit 2.
is that telling us which program we're using?
What do you mean?
You know, most of the time the book tells us, hey, and you in ProLogic 500, you can do this, and
I don't remember. So it's in there. I don't remember seeing that.
a lot of times, you know, when it's telling us about the bits, it tells us like in the SLC5 series program, like that 512, you know, it tells you. But when it gets down to that, I don't see anything telling me where I can do this in the 500R.
Well, this is we're programming with RS Logic 500.
Okay.
So everything in this book is written for RS Logic 500.
500, okay.
All our PLCs down there will program on the ones that we have available. We have some new ones that we don't have enough of them to do. I think we got a 5,000 down there, and another one that we can't even program with this language that we're dealing with now. Everything's going to be similar, right? You understand that. But what they do is they add the text-based language where you can actually type in your commands, where you have to put the ands and the ors and all that kind of stuff. You know, RS Logic Pro doesn't support that. Now, Siemens 7, the Step 7 software we got, when you start your program up, if y'all remember, I know that was a long time back, you specify which programming language you want to program. And the one we used was Ladder, but they have, I think, STL and another one that's available for programming. So PLCs usually give you a couple of ways to program, and that depends on the programmer. You'll find out a lot of programmers like the more difficult the language for people to learn. If they know it, that's the one they're going to program. Wow. Yeah, I guess everybody else confused. Thank you, Miss Moore. There's a programming language, an operating system called Unix, which still runs the internet, by the way. And it's a very complicated language to learn. But it'll probably run the internet our whole lifetime. There's still people out there programming in COBOL, which is yeah, a lot of the big companies have been using stuff for years. But see, the 0 bit's not working, but on this simulation, but the program itself is. So what I can do is, if I use the right mask, so which bit do we want to see if it's set or cleared? So input 2 is my mask. Input 1 is what I'm trying to figure out what's going on. So right now we're looking at bit 6. So I can come up here, let's say bit 11. I want to see if it's set or cleared. Okay. So here it's cleared, right? You understand? Here's a 0, here's a 1. So if I get back a 0, what does it mean about, and I could come up here and what's it doing with all these other, this guy's closed. Well, I'm not checking that bit. I'm not checking this input. I'm not checking this input. I'm not checking that input. I'm not checking 4. I'm not checking 5. I'm not checking 6. I'm not checking 7. I'm not checking 8, 9, 10. I'm checking to see if this guy over here is either giving me back a what, if it's either open or closed. Right now, my 0 flag's not working, but it should have worked. If this bit comes up to be set, that means that sucker is closed, right? You understand? If it comes up and gives me 0, it means that is what open. So what I'm doing is I'm masking off the input. So this is my actual input over here, and all of them red, these return what? These are giving me a known or a true, but I'm not checking those. Now, as soon as I close switch 11 over here, then what did my AND give me back? Again, indicating it's not 0 anymore, so it indicates that that's closed, right? I come up here and do this. Yeah. So we do these masks all the time. I mean, just to strip off things, and we get in all this information, you know, from thumb wheel switches. Thumb wheel switches are going to give you back all this information at one time, right? You understand? But you're trying to see if this one bit is changed, right? You understand? Inputting in groups and outputting in groups becomes very important. Instead of dealing with one bit at a time, what can we do with these instructions? We can deal with 16 bits, 16 at a time, or even 32. If I wanted to AND 2 of them together, I would just take the ANDs and the ORs, right? You understand? So what I would do is I would AND these two and I would AND these two, and if they both came out to be 0, it indicates that the bit that I'm checking for, or the bit, yeah, is open. So we can combine these things to figure that. Or what do we do with ORs? So ANDs, we can use it to clear a bit. ORs, we can use it to see if a bit is a 1 or a 0. Or we can use it to make sure a bit is cleared, or we can use it to make sure a bit is cleared. We can't use it to make sure a bit is set, but we can use it to make sure a bit is cleared, right? So let's see if we can always make sure 11 is cleared. So I'm going to come up here and AND it with this number right here. But so this is my mask. So I'm checking to see, I'm going to make sure bit 11 is always clear. Bit 10 is always clear. So right now it's running, and no matter what I do with 10, the value doesn't change, right? See that?
Why?
Because I'm telling it to ignore it. If I come up here and change this one, the value changes. I've got my scan rate set real low. I thought that might hit my ANDs. Okay, so I'm telling my PLC to ignore bit 10. So I'm over here on my input, I'm changing bit 10 all day long, and it's not doing what? It's not doing anything. Okay. If I come over and change bit 12, should the value over there does what? It changes. So what I'm doing with this AND is no matter what is going on over here, I've opened up my mask for that bit right there, and now 10 is stripped off. That makes sense?
So if you're gonna ignore one, you got to do like 7 and 8 together, or 8 and 9 together.
Now what we do is we come up with a mask that's saying, okay, I want to ignore a bit. For whatever reason. Okay, I want to ignore a bit. I should have another PowerPoint open up that's got a blank slide because it keeps messing me up. And that way I can come to this one all the time. Instead of dealing with 16 bits, we'll just deal with a smaller number. Now let's say I'm bringing in an unknown. And no matter what that bit right there is, I want the other ones to come in unaffected. But no matter what this thing is right here, I want it always to come in as 0. Well, what I would do is I would come up here and I would do that math right there. So what would this be right here? Well, no, it's going to be whatever x was, right? What would this be right here? What's this going to be right here? What's this going to be right here? So up here, if x was a 1, it would be a 1 here. If an x was a 0, it'd be a 0. But what I just did is I just did what? I masked it out.
And what mask are you
Man,
using?
not or, because the or says any. Yeah, so if I came over here and did this with an or, so let's say this is an or mask, and I use the same mask. Then what's this one gonna be? What's this one gonna be? I'm sorry, you're right. Sorry, Seth.
You did say or, didn't
Yeah, I did say or. So this would be a what? This would be a 1. This would be a x. Now this would be a what? Or. Well, let's say no matter what's going on, I want this bit right here to always be a 1. And what or math would I use? So what would this one be right here? X. What would this one be? X. This would be a 1, no matter what x is, right? And then what would this be? And this would be a what type of mass? It's been or mass. Yeah. So I got a PLC that's only got 10 inputs. All right, you understand? I got 10 inputs. And I'm trying to see if a bit is set or cleared. Well, what's those unused? But I'm going to bring in a 16-bit word. So even if my inputs, even if I only got 10 inputs, when I read these registers or I load that input port in, I'm going to get in a 16-bit word. Right? You understand? So what if we wanted those unused bits, what if we wanted to always be 1 for some reason? Well, we could OR it, right? What if we wanted to make sure they was always 0? Then we could do what? We could AND. So these guys are used a lot, especially when you come in and you start examining individual bits of a 16-bit word to see if that certain bit is set, whether that certain bit is cleared, whether you want it always cleared, you want it always set. For whatever reason you use it for, these are available to you, right? So what we would use the overflow for, I don't see anything we would use that for. I mean, I'm sure, because when is the overflow set? Overflow is set normally when the sign of the number changes. We exceed the range of our numbers. Okay? So that means if I add two positive numbers together, I should get a what? Positive answer. Which makes sense. But the problem is, if I add two positive numbers, and we'll go back to, so let's say I'm going to do 4-bit numbers. And I'm going to add this positive number. And what we're going to do is we're going to use this as the sign bit. So right now this would be considered to be what? Positive. And I come up and add it to that right there. This is considered to be what? Positive. Well, let's add them. Well, this is going to be 0 with a carry 1, 0 with a carry 1, 0 with a carry 1. And it says my answer is what? It says it's negative, but it's not. So what I've just did is I tried to put in my math, I've come up with a number that exceeds the range of what I can do. So I need to know that, right? You understand? That makes sense. So this would be an overflow. So what we've done is we've exceeded the range that our math registers can hold. And we could do the same thing. So the overflow means your register that's holding your results we've exceeded the range of the numbers we're trying to hold, right? Does that make sense? Well, the carry flag, what's the carry?
Generator.
Now this would set two flags, by the way. So if I add these two numbers, what would this be?
One. Real. One way that way.
And we'd get a 1 in our carry, and here we would get a 1 in our V flag too, right?
One of what? You said the same on B.
The V, because I added two negative numbers. That might be right. Need to see that. So this would be a -8. This would be a +9. So no, we didn't exceed. So the V flag wouldn't be set. Now this is a -8. This is a +9. If I add a +9 and a -8, what do I get? +1. So the V flag wouldn't be set. But the C flag would be set because what did I do? So this, if we consider, so this would be a -8. If these were considered unsigned numbers, this would be a +9. This would be a +8. What would my answer be? 17. The biggest number we could possibly have in 4 bits is 15. So I just did what? But we have an indication of when that happened because we get a carry. The microprocessor supports what we call an add with carry. I just feel like it looks so we can take numbers out with whatever resolution that we want.
So, could I have another little status file up there with the carry, all the carries in it?
No, we got one status file that's used for every operation. So what you got to do is that every time you do it, you got to check it after this operation. So all our math uses the same status register, right? And all our logic uses the same method, right? You understand that? So what happens if I add and then don't check for a carry right after the add, and then I do a logic, then your status register is going to be set according to the last instruction that was executed when you checked. Y'all understand that? Yes or no? So the math right here, what would happen if I add these two numbers together? Well, my C flag would have been what? My carry would have been what? A 1. My overflow would have probably been a 0. I didn't overdo the sign, right? You understand? My sign flag would be set at what? No, this is where your registers are set up. Your status registers are set up not by the numbers that's in the instruction. It's set by the answer of the instruction. Okay, y'all understand that? So if I look at this right here, now what we did is that, okay, I added, this would be a -8 plus a +9 if I'm using sign numbers. If I'm not using sign numbers, then this is going to be a 9 and a +8, right? You understand? So what does the flags do? Well, the flags, all they do is they come in here and they're looking at the results of the operation, not the two operands. They're looking at the answer, right? Y'all understand? And they're going to set or clear depending on the answer. it's up to the programmer to decide what to do with with these flags. Y'all understand that? So they're being said and cleared this whole time, but it's been nothing to us because we haven't said, okay, did I get an overflow? Did the sign change? Did this happen? And what you will have to do is you would have to put an instruction in there that says, okay, if I got an overflow, what do you want to do? Yeah. Right? You understand? So in my Logic Pro right here, so right now, this is considered to be a positive number. So my sign would be a what? 0. So right now, these are the flags these are the ways these flags would be set. But then it's up to me to come in, and Logic Pro don't work. It's to put an instruction like this. Okay, so if S2 word 0 bit 2 is set, then do something. Right? You understand? Here, what I was going to do is turn on an output. But you could come up here, you could clear it, you could set it, you could jump somewhere, you could jump over here to set and do a certain program if that bit comes up to be set, right, or cleared. So it's up to you to do what? It's just like a counter. The counter, once it's done, it generates a done bit, except that done, instead of me addressing it as a bit, it's got a name, right? If I don't use that done bit somewhere, right? So how do we, timer timing? Have y'all used that one? But you have to use it.
Program.
Your programmer has to use the timer timing. You have to say, okay, what do I want to do if this and came up to give me a 0 answer? Then it's up to you to do what?
Whatever you gotta do.
Yeah, do what you gotta do. So these single bits are these status registers. If you wanted to do something if you had a carry, if you want to do something if you had an overflow, if you want to do something if the number was negative, is that you have to program it in, right? You understand? But just like when we used that S214 or whatever it was, that bit's been up there flashing the whole time. But it was never used until what? And you assigned it and you said, okay, this is what I want to do on that. So the way, if this thing was working, if Logic Pro was working right, if this came up to get a 0, then this sucker right here would light up. Right? You understand? Output 4. If it wasn't a 0, then output 4 would be turned off. Or 4 is 0. That might be my phone. Oh, output 4. So output 4, you can't see it. It's over here. And then get 0. So that's the way the thing should work. What I might do before our next class is come up with something I can set up on the 1100 on one of our inputs and then try to make this thing work because it would be interesting. So if I wanted to find out if I was an overflow, then I would have a contact over here that's use what? S2, 0, flash, what's it? 1, right? But if I wanted to do something because I got a carry. 0. So I might take my answer, take another one and add 1 to it if I had. Y'all understand what we can do? So right now, what's my integer math? My integer math is 16 bits, right? Or if we do a long word, it's 32 bits. But what if I did math and I'm dealing with positive numbers and I wanted to extend it up to 64-bit math? Could we do that? Yeah, if I picked up the carry on my next 2 numbers, right? You understand? And if my carry was set, I would add 1 to it, right? You understand? If my carry was cleared, I would add 0. And then I would add it to my other number. And now all of a sudden we got 64-bit math, right? Microprocessor support what they call it add.
When you do that, do you want to do for the sign?
Well, we said, that's what I said, positive number. If you were doing 64-bit math, then you would check the second group for your sign. Not your first group, you would set your second group for your sign. All right, does that make sense? So what you do is you just go ahead and add your first numbers like they're unsigned numbers. And don't even pay any attention to the what? To the sign file. If you add your next two numbers together, then that's where you would look at your size and you'd look at your overflows to see if you overflowed right. That was a real good question. So how would I come back in and do my other? So these are our logic functions. We got ands, we got nors. So let's see what's the next one is. We got to move on, guys. Yeah, y'all go ahead and take another 2-minute break. No. Yeah, Wednesday be allowed. I know these long lectures. And I keep exclusive ors and then not. So how do we get the nans, nors, and all of those? Yeah, so figure 13.3, and unfortunately the Logic Pro does not give us inputs, and we don't have time to go up there and set up all these inputs. Yeah, 13.3, page 278. So 13.3. Of course, y'all can see it just as good as I can bring it up here. So y'all can see how that works.
Do any of the PLCs allow you to have more than 2 voices? I mean, like you wanted to have like 3 sedans, there many PLCs offer that?
Not that I know of, because you're going to AND a source A and a source B. Well, the source A and source B, I'm not gonna, I've never seen it.
Right.
But I learned a lot of things, the technology that we're in. But these are computers. Every computer I've ever dealt with can only work with two words at a time, or two double words. But what we can do is we can cascade them, right? You understand? So if I needed to AND three words, then I could AND 2 and then do what? Take the answer of this and then AND it with the next one. And we could keep going and get as many ANDs as we want to. It says Logic Pro is already running, but it's not showing up on my taskbar. There we go. So this is where I need to load it from. So if we wanted to do a NAND, what would we do? Yeah, in 2 different rooms, right? So ANDs and ORs are considered to be output. I know I told you that wrong at the start of class, but they're considered to be output. But what we would do is notice here they're taking D3 0 and it with D3 1. They're storing the destination in D3 2, and then what they're doing? Yeah, they're going to D3 2, and then they're not, and you send it back to D3 3. And this performs a what type of operation? A NAND.
Whatever comes out the hand, converted.
Yeah, so this is the way we would get our NANDs and our NORs, and our exclusive NORs. We just do it regular, and then we would put the next run, we would knock the results. Alright, does that make sense? So what we have now is all the basic logic plus your exclusive logic. So I can do a AND, I can do an OR, I can do a NAND, I can do a NOR, I can do a NOT, I can do an exclusive OR, and I can do an exclusive NOR. Well, the exclusive ORs, so a NAND would be an AND and a NOT. A NOR would be an OR and a NOT. An exclusive NOR would be an exclusive OR and a NOT. Is that what you meant?
Not so.
Yeah, the NOT. This is just showing us the bit register. So this would be a what? NAN, right? This would be a NOR, combination of that. This would be, so it's a NOR. These are the status flags. It's up to you to determine if you're going to use all these, right? Y'all understand that? So you can set up a contact just like you do with that the flashing register. And I can't get it to work in Logic Pro, but if I have time, guys, I'm gonna be here all day tomorrow and nights. By the way, if you're going to attend the press conference tomorrow, it's now at 2:00.
Oh, it's 2:00.
Yeah, it's 2:00 now. Okay, guys, let's get over the shift instructions and then we'll be through. So we got two ways we can shift. We can shift left or we can shift right. And what do you think that would be?
Flashing arrows showing that one lane of the highway is closed due to construction.
No, what they're saying is that on these signs, we can use these to actually point, so we can make a lights flashing sequence and move them over to that. I don't know if y'all remember Knight Rider. Knight Rider. Yeah, that was one of our projects we used to do with microprocessors. We would have 8 LEDs up there, and we'd shift it to the left until it hit the end, and then we would do right. So we could shift it right, and we just salute it.
Oh, that's just like we run a light on the car.
Yeah, and a lot of these things used to be done with rotary relays and stuff like that, but the problem is with these rotary relays is they wear out real fast.
Runway lights go like that.
The runway lights go in sequence like that. When the plane's coming into the land, we'll have them lit all the time, and then they shift a 0 through there, so they strobe a 0. So instead of a strobe and a 1 through there, they strobe a 0. And it's just what? Yeah, that's all it is. But all it is, if they're doing it with a PLC, all they're doing is just shifting a bit on an output port, right? Very easy to do. Often used to control display signs in a plant, in an outside, flashes, arrows. We used to use these originally when the microprocessors first came out. They supported 2 math instructions. Well, actually 3. They supported addition and subtraction, and then complement. And what's complement? Just changes the sign, right? Or just switch your or 2's complement. So we had to write programs that divide, and that's what you would do. Is you would start taking your divisor and you'd shift it, and every time it would move into the carry bit, if it was a 1, you would subtract the divisor from the what do they call it, dividend, or not multiplication. The quotient is the answer. So we have the divisor, we have the subtraction. But anyway, we every time we saw a 1, we would subtract the divisor from it, and every time we had a 0, we would shift another one in. Does that make sense? It was really neat. But we had to use these to actually do division and do multiplication. So instead of doing multiplication by repetitive addition, we would literally just shift it. And then we'd check to see if it was a 1. If it was a 1, we would add it. If it wasn't, if we was multiplying, if it's a 1, we would add it. If it wasn't a 1, we wouldn't do what? We wouldn't do it. And that's the way we did multiplication, is by examining each one of those bits. So what we can do with shifts is we can examine each individual bit. And every time we come up, and if we see what we want to do with this bit, then what we could do. we could shift another one over there and then see, okay, what do you want to do with this? And then shift another one there and say, okay, what I want to do with that. And what we could do is we can make a decision on what to do depending on if a certain pattern or whatever was coming in off these inputs or out of these files. Here they're talking about flashing lights. They work real good for that too. So here we're going to bit shift left. So let's look and see what information we put in here. First of all, this guy uses indexed addressing. So bit shift uses nothing but indexed addressing. So get out your addressing mode and see what this is. How do we identify it as indexed addressing? With the hashtag. What we used to call it the number sign. Everybody calls it a hashtag.
I moved to pass.
Huh?
I already used it.
So let's look at what does it say index addressing is. So it says index addressing, we're going to use a register inside the processor that we call the index register. The index register is a pointer that we can offset from. So didn't I give you all that thing on addressing mode? Okay, so what does it say about that? What is the index register?
Which one, the end?
S, it says S24. So S24 is 24 in the status register is your index register. It's a 16-bit register that I can load with anything. I understand. Yeah, it's an integer. Unsigned integer, by the way. So the only thing we can do is offset forward. We can't offset backwards. So up here I say, okay, I'm going to shift left some file somewhere. So this cannot be a constant. This is going to have to be, this cannot use immediate addressing. Can't even use direct addressing because it says we must use what index addressing. So what this is going to take, whatever's in the index register, which is 24 inside the static register, and it's going to add this register. And that's going to be the address of the object. I understand that. Yes or no?
Contents of the index register is going to add 0.
Yeah, whatever you put there. We call this the offset. So right now we're doing what?
Okay, so that's not the whole GAMUT?
That's not the address.
Okay.
So what it would do is if I just say B3. So where's it going to get the information from? It's going to get it out of the B3 file somewhere.
It's 0?
I don't know.
Okay, close.
So let's say S24. What is it? The whole thing just says 24, right? It's a 16-bit. Okay.
That's over.
So this is what we need to do. So this is current file. So let's say my index register, what do you want to put in the index register?
5.
Okay, so let's say we'll put 5 in there. So what I would do is somehow S24, I'm going to set it to equal 5. So my instruction is this, B3, colon, and then what does it say? 0. This right here is the offset. So my address would be B3, colon, 5. Well, what if this right here was a 2? Then my address would be B3, colon, 7. So what we do is we take the contents of the index register and we add an offset to it.
So the hashtag still fall down to B3.
No, this is the actual address. This indicates, the hashtag indicates we're using index addressing.
Okay.
But what is the address? The address would be It's gonna be in the B3 register, it's gonna be in the, B3 data file somewhere. Right, you understand? To find out where it's at in B3, there is no such thing as a hashtag B3 data file. We have a B3 data file, and we can have 256 of them, right, you understand? What index addressing says that if it says that, if the hashtag is in the instruction, it's going to take, to figure out where it's at in the B3 file, it's going to take the contents of the index register, which is S24, it's going to add that, it's going to add the offset to that, and the results is the address of the operator.
3, 5.
5 for the first one because we're using an offset of what? 0. Now next time I said, what if I change the offset of 2? Well, now all of a sudden my address, the actual address is B3:7. It's the whole word, right?
The hashtag pretty much just tells you
Index register. So just looking at that, you have no idea what address it's going to use unless you know the contents of the index register. If you don't know the contents of the index register, it's not going to do you good.
So you say it holds the number, and then when I put another number in, it changes, it adds it up. Is that what you're saying?
What do you mean?
You went from 5 to 7.
Well, I changed it to 2.
Yeah.
Well, I changed my instruction.
Well, 0.
So I've got 2. So let's say I use the instruction. Let's say I use a B3. Let's say I use a :8. Okay. Then what would be the address of my operand? Well, I have 5 in my index register, right? I'm gonna add that to it, so that would be the address of the operand. So what do? If we see this one, what address is it? I have no idea, unless I know the contents of the S14 register. But how does the S14 register get something in it?
You assign it.
Yeah, you put it in there, right? You can load it. You can load it with a immediate addressing. You can load it with a number using a move instruction. You can load it with an input port. So what's neat about loading it with an input port is I could literally change where my table is depending on what you input into it.
Okay, now, give me an actual application.
What we're trying to do, normally we use the index register to automatically go through a table. We're not going to necessarily do it here because all we're going to do is shift a bit to the left or the right, and they designate that we're going to use a B3 register. I mean, using what address am I? Index address.
So that would change your output, wouldn't it? If you shift the bit.
No, we're not going to shift the index register. We're going to shift the address that the index register points to plus the offset. No. This guy? Yeah, that's what I'm saying. We can use it. This guy was shifted to the carrier bit. So I could take a 16-bit word and I could shift it into the carry bit, and I could actually do something for every bit. So I could say, okay, if I shift a 1 in, I'm going to do this. If it shifts a 0 in, I'm not going to do that, right? You understand? So what we can do, we can literally examine all 16 bits of a 16-bit word, one at a time. It's just every time through the loop, we would do what? We would shift it.
Does the scan rate fit how fast it gets through these numbers, or will it cause the scan rate?
The scan rate always affects everything. So what you need to do is, normally when you look up instructions for a processor. So what we'll do, let's see if I still got it up. Oh, here we go. I just went right past it. Okay. Well, I come in here and start looking at these instructions, and this is the actual instruction set reference for the 500 versions of these PLCs. We see if it shows it here. It might not show it on this one. This is a pretty block transfer, data handling, math. Don't know where logic would be at. I'm going to see if it shows it. If it's not, I'll show you on 1100. What it normally shows you when it gives you the construction is it gives you the, no, this don't. But if I looked up the 1100, what it does is for every instruction, it gives you the amount of time that instruction takes. And normally you get a different time if it's true and a different time if it's false. And if you knew all the instructions in your program, you could basically have a good idea of what the scan time would be. This guy here don't show you that. But it does show you the flags. I didn't see the logic. Do y'all see logic over there? Oh, probably data handling. There's your nots, your nans, your nors, you know. And we're dealing with, I don't see the bit shit. I don't see the bit instructions in here. They're not in data handling. Here's all your logic instructions right here. What's that? Yeah, this is the one we'll talk about. This is in the next chapter where we actually can put a mask inside a move instruction. But y'all understand the mask now, right? I don't know where the bit shift instructions would be, guys. But this is what I wanted to show you, Larry. See, so this guy here, this move instruction on 1100 would take what? For a word, it would take 9.18 microseconds. If it was true, it would take 0.87 microseconds if it was false. There's our interrupts, program control, sequencer, compare.
Programmer Joe had to jump in.
I'm listening.
There's a lot to this.
I looked at logic. I just looked. So the only thing here is our ands, ors, nots, nors. Let's get through with what this does, and I'll try to find them inside there. So we have, what's R6? 0. Okay, so this keeps up with our status, right? So this don't use a status register bit.
Then this right here is, this is where we get our original number from. So if I wanted to shift a 1 through here and flash the light, then we would make sure that D3, this is our bit address. This would contain the original bit that we're going to shift through. That makes sense?
Yeah.
Then the length, this is how many bits we're going to shift. Everybody okay? Yes or no?
Or we don't have to move them people forward.
Alright, we could basically shift any group that we want to. Now, it's gonna shift the entire 16-bit word. But what it determines is it determines what goes along with this bit right here at R6 that they call what?
How that?
But,
What's it with?
this is called the unload bit.
Unload.
So what that means is, let's say I started, how many bits are we shifting? 7, I think we're shifting 7. I know it's almost time to go, guys. I know y'all. The class does go to 30, right? So let's say I'm going to shift this number right here. We're just, how many bits are we doing? 7 bits. Okay, and let's say in my file that I'm shifting in, I have a 1 there. I forgot which one it was, B something. And then sitting right here is the unload bit. So I'm going to shift it once. What's going to happen? This is going to go into the unload bit, right? This is gone. This bit right here will come right there. Okay.
What is that bit down there?
This was our load. This is what we started off with. No, it's going to do it forever unless we decide to do what we wanted to do.
So is that actually?
This is the bit number. This is what we're going to load it with. Okay, so this is what I'm shifting in. If I'm doing a shift left, we specify what we want to put in when we shift it. And I specified a what? A 1. Okay. Let's say I shift it again. My unload bit would go to 0, right? This is gone. It'd be a 1, 0, 1, 1, 0, 1, 1. Where'd the 1 come from? That's the bit that we specified we want to shift in. Okay? Everybody understand? Okay, we shift it to the left again. Then what? Then my unload bit would go to a what? 1. This bit's gone. 0, 1, 1, 0, 1, 1, 1. Okay, you understand that? I shift it to the left again. My unload bit is going to go to what? 0, 1, 1, 0, 1, 1, 1, 1. So we specify the bit that's going to come in on this side over here.
Oh, okay. So that's not going to change unless you change it.
Unless you change it.
So eventually you're gonna end up with all
1.
Right. After 7 shifts, we would end up with what? All 1. Now you have to understand, this guy right here is still going to shift. You're losing the entire 16-bit word. So if I was going to go, if this is bit 0, 1, 2, 3, 4, 5, 6, 7, then bit 8 here would have went to a 1. Because it's going to shift the entire 16-bit word, right? And if I shift 16 times, I would end up with all 1s. But what we're trying to do, when we specify the length, we're specifying where the unload bit is. So it's going to, so the unload is going to follow this bit right here every time we shift, right? You understand? Now the entire 16-bit word is going to shift. So all we do when we specify the length, if we specify what's going to set, what bit is going to set and clear the unload. That makes sense. And then we decide to do, this is the guy we're going to monitor right here. This is what we're going to do. We're going to do something if it's a 1, or we're going to do something if it's what? If it's a 0.
if I wanted to shift the zero through, I might start it with all ones, and then I would set this to zero, and I shift the zero through, right? Okay.
That's the shift bit, right in that box, on the bottom right.
Now, but you have to understand, this shift bit can come from anything.
Right, but that's what it's called, the shift bit, and the one at the top left is the unload bit.
What would happen if my shift bit was specified as the unload bit?
Well,
What if I told it my shift bit was my unload bit?
so it would change all the time. Or we shift it right?
It would do what we call a roll or rotate. It would rotate left. Y'all understand what we just said?
The shift bit was
If my unload bit was my original bit. So let's say my unload bit is, and we start off with the unload bit being a 0, and then I started off with this right here. But I specified as this being my shift bit. Okay, I'm going to shift it to the left, and whatever's here is going to do what? Come over there, and then this is going to shift into the bit.
So,
Yeah, we call this a rotate. Rotate left, rotate right. So if I wanted to rotate it, if I just use a bit, it's going to load that bit all the way up either left or right, right? You understand? That makes sense. Yes or no? If I take the contents of the unload bit, and then I just use it as the bit, then we can do a rotate left or we can do a rotate right. So that means if I was going to make a sign flash like that, right, you understand, just in a loop, I would maybe load it with all fives, right? Or maybe even 1 5, depends on how many lights I have out there, and I'd load 1 0 1 0 1, right? You understand? And then I would take the contents of my unload bit and do what? Loop it back around. And then we can make a sign go this direction, we can make it go that direction. We can make strobe lights at the airport, just constantly do what? Strobe, load it with all ones and shift a 0 through, or load it with all zeros and shift a 1 through. Alright?
Or if I make it go like that, go all the way to the top, and then bring it back, go on both sides, first back.
And you have to make some awesome Christmas displays.
Oh yeah, awesome Christmas displays.
Come see your,
You make it go this way look for a little while, then you use timers to make the shift and go back the other way. And what you'd be using for your output would be output port, right? So yeah, you can put on some impressive Christmas lights that are filled with.
how do you put it to me?
Well, what you do is you would hook up a microphone to one of your inputs, and then every time you got like a bass beat, you cause it to chill. Because that's usually what you see, right? They got some very, very impressive slides. And I think one of the slides said the guy did it with a PLC, or more than one, really, because he was controlling lights all over his house. And he had these things that looked like they were jumping, you know, and then they'd go back the other way. He was an engineer that set that up. So what other bits do we have besides the unload bit? Let's look at that real quick. Make sure we're not screwing that up on. See what else? Whatever we have in that R6 register. So we have a bit shift left, bit shift right. Control register 6 length indicates the number of bits to be shifted. The shift bit instruction that shifts the bits in the data file to the right or left. It could be either what, a low or high. I don't even see on my PowerPoint where it talks about that UL, that unload bit. Does it talk about it in the textbook?
284.
What's that?
284. Where,
So we got an R6-1 is the what?
Control.
Okay, here we go, starting on 283. So R6/done, that would be the done bit, right? R6/UL would be the what? Unload bit.
I see something like that on page 280, about the last sentence. Note that the unload bit R6 0 slash UL place on to 300 slash bottom of page.
Oh, yeah. Very bottom, last sentence. So they didn't put a group here that told you the bids. You can look at the data, look at the instructions on those manuals, and it will tell you all the registers that are controlled. But what we do, the status register for this one, or the control register, is not in the S file. It's, you assign it one of those control register files, right? And you do that inside the bid shift instruction itself. So right now they're saying, okay, the control register for this bid shift right is R6 :1. And once you assign this word, then we do an element addressing. We don't have to know the bits because the bits have a name, right? So the UL is the unload, the DN would be the done. So after it shifts that 7 times, the done bit would go